Welcome to the deep dive.
Oh,
We're here to really get into the heart of the sources you share with us.
that's right.
And today, well, we're tackling chemistry. It gets called the central science for a reason.
It really does. It connects so many fields.
Yeah, from physics way out in space to, the biology inside us, even the medicine we take. It's all chemistry at some level.
Absolutely.
So our mission here is to give you a real shortcut, not just a quick summary, but a genuine understanding of chemistry's big ideas.
Mm-hmm.
We're leaning heavily on chemistry, Atoms First, the third edition by Burge and Overby.
A solid source.
We want to unpack matter, measurement, and all those amazing changes that shape everything. Might even find some surprising bits along the way.
And that's the goal, right? To get past just definitions.
Yeah.
We want you to really grasp why these things matter.
Exactly.
You'll see how fundamental ideas like the scientific method we'll talk about aren't just textbook stuff. They've led to huge breakthroughs.
Yeah.
Well, the source mentions using gold nanoshells for cancer treatment. That's chemistry in action, impacting lives, starting from understanding the basics.
Okay, so let's start there. The basics. Chemistry is fundamentally the study of matter and how it changes.
Right. Matter being, well, pretty much everything.
Anything with mass that takes up space.
Mm.
Your body, the air, this device you're listening on.
But the really fascinating part is the change, how things transform.
And that's where the scientific method comes in. It's like the rule book scientists follow.
It's a process.
It kicks off with careful observation, doing experiments, gathering data.
Just seeing what's there.
Then comes the thinking part, spotting patterns, finding relationships that seem reliable.
And you summarize those patterns into a law.
Right. A law just says what happens. It's concise. Like, if I drop this, it falls.
But it doesn't explain why.
Exactly. So the next step is forming a hypothesis, a sort of educated guess.
A tentative explanation, yeah, based on what you've seen.
And here's the key part. You test that hypothesis rigorously. Lots of experiments.
Over and over.
And if it holds up, if it keeps explaining things and predicting outcomes, it can become a theory.
And a theory isn't just a casual guess, it's a big deal in science.
It's a unifying principle, right?
Mm.
Explains lots of observations, laws, predicts new stuff.
But it's not set in stone. Theories are always being tested, tweaked.
Or even thrown out if the evidence points elsewhere.
It's dynamic, always learning.
It really is, and you see this playing out historically.
Oh, absolutely. Take Edward Jenner back in the 18th century. His work on smallpox is a classic example.
Milkmaids, right.
Exactly. Jenner observed that milkmaids who got cowpox, which was pretty mild, they seemed immune to smallpox, which was devastating.
Just an observation at first.
But it led to a hypothesis. Maybe getting cowpox deliberately could protect you from smallpox.
Risky idea back then.
Extremely. But he tested it. Famously gave a boy cowpox, then later carefully exposed him to smallpox.
Same.
And the boy didn't get sick. The hypothesis held. That led to vaccination.
And eventually, the eradication of smallpox globally. Wow.
A huge medical advance, all starting from observation and testing a hypothesis. The scientific method in action.
That really shows the power of it. And in chemistry, we're always kind of juggling two perspectives, aren't we?
What do you mean?
The macroscopic, the stuff we can actually see, like wood burning or iron rusting.
Okay, the visible world.
And the sub-microscopic or molecular level, the world of atoms and molecules doing their thing.
Right, the unseen processes driving the visible changes. Chemistry connects those two.
Yeah, it's like the behind-the-scenes look at how reality works.
And to get that look, you need data, precise data.
Which brings us to measurement. So crucial in chemistry.
Can't do much without it.
Pretty much everything we deal with is a quantitative property, something you measure.
And the measurement needs a unit, always.
Right. Saying a pool is 10 deep is useless. 10 feet, 10 meters makes all the difference.
Absolutely, which leads to standardizing units. Think about the mess before the SI system.
The International System of Units, adopted in 1960, right?
Yeah, to get everyone speaking the same scientific language. Before that, confusion reigned.
So there are 7 base SI units.
Yeah.
Length, mass, time.
Kelvin for temperature, the mole for amount of substance. The key is they provide a universal baseline.
And the prefix system is just elegant.
It really is. Tera, giga, mega, down to nano, pico. Makes handling huge or tiny numbers consistent.
Prevents disasters, too. Didn't a Mars orbiter get lost because of a unit mix-up?
Sadly, yes. A very expensive remander that units matter a lot.
Okay, let's talk specific measurements. A common confusion. mass versus weight.
Oh yeah, people use them interchangeably all the time.
But they're different. Mass is the amount of stuff in an object. It's constant.
Doesn't matter if you're on Earth or the moon, your mass is the same.
But weight, that's the force of gravity pulling on that mass.
So you weigh less on the moon because there's less gravity, but your mass hasn't changed.
And the SI unit for mass is the kilogram, but in the lab.
You're usually using grams, 1,000th of a kilogram, just more practical for lab scales.
Then there's temperature. We bump into three main scales.
Celsius, Kelvin, and Fahrenheit.
Celsius is what most of the world uses day to day. Water freezes at 0, boils at 100. Simple.
Makes sense.
Kelvin K is the science one, the absolute scale. 0 Kelvin is absolute 0.
The theoretical coldest possible temperature. No negative numbers on the Kelvin scale.
And what's neat is that a degree change in Celsius is the exact same size as a Kelvin change.
Right. K equals degrees C plus about 273, so it's an easy conversion.
Like body temp around 37 degrees C is about 310 K. Easy enough.
And then there's Fahrenheit, degrees F, mostly used in the U.S.
Water freezes at 32 degrees F, boils at 212 degrees F, a different scale altogether.
Yeah, 180 degrees between freezing and boiling versus 100 for Celsius. The degrees themselves are different sizes.
Requires a formula to convert between degrees C and degrees F.
Which we won't bore everyone with right now.
Good call. Now, besides base units, we have derived units.
Right, combinations of base units, like
Right.
volume. The official SI unit is cubic meters, M, which is huge.
Massive. Not practical for beakers and flasks.
So we use liters, L, and even more often, milliliters, ML.
And conveniently, 1 milliliter is exactly 1 cubic centimeter, CMLO. Very useful.
That brings us to density, super important property.
Absolutely. It's just mass divided by volume. How much stuff is packed into a space.
D equals M over V.
SI unit would be kilogram, but again, not practical.
So we use GCML for solids, usually, or GML for liquids.
Makes sense for typical lab amounts.
And density explains some cool things, like ice floating.
Ah, yes. Very unusual behavior for water.
Most things get denser when they freeze, right? They shrink.
But water expands. Solid water, ice, is actually less dense than liquid water.
Which is why it flows. If ice sank.
Lakes would freeze solid from the bottom up. Life wouldn't survive winters in many places. It's a crucial anomaly.
Okay, so these measurements, they aren't always perfect numbers. There's uncertainty.
Always. Which leads us to exact versus inexact numbers.
Exact numbers are, well, exact, defined values, like 1,000 grams in 1 kilogram or 12 in a dozen.
Or counted numbers. If you have 28 students, you have exactly 28. No uncertainty there.
They have infinite precision, technically.
But inexact numbers come from any measurement. Length, mass, volume, time.
Anything you measure with an instrument.
Exactly. And every measurement has some limit, some uncertainty. You can't measure something perfectly.
So how do we handle that? How do we show that uncertainty?
Through significant figures. Or sig figs. They tell you which digits in a number are actually meaningful.
Okay.
The basic idea is the last digit you write down in a measurement is the uncertain one. It's your best estimate.
Like if I measure something with a ruler marked in centimeters.
Right. You might know it's between 2.4 and 2.5 centimeters. You estimate the next digit, say 2.45 centimeters.
That 5 is the estimate.
That 5 is your uncertain digit. Writing 2.45 implies your uncertainty is in that last decimal place.
So you report all the digits you're sure of, plus one estimated digit.
Precisely. It communicates the precision of your measurement. You don't want to overstate it.
Makes sense. But figuring out which digits are significant, especially with zeros, that can be tricky.
It has rules, yeah. Let's break them down quickly.
Go for it.
1. Any non-zero digit is significant. Easy. 112.1 has 4 sig figs.
Okay.
2. Zeros between non-zero digits are always significant, like in 305 or 50.08.
Got it. Trap zeros count.
3. Zeros to the left of the first non-zero digit are not significant. They're just placeholders.
Like in 0.0023.
Exactly. Only the 2 and the 3 are significant, so 2 sig figs there.
Okay. Leading zeros don't count.
4. Zeros to the right of the last non-zero digit are significant if there's a decimal point anywhere in the number.
So 1.20 has 4 sig figs.
Yep. Those trailing zeros after the decimal tell you the measurement was precise to that level.
What if there's no decimal? Like the number 100?
Rule 5. That's the ambiguous one. Trailing zeros without a decimal might be significant, might not. 100 could be 1, 2, or 3 sig figs.
So how do you avoid that ambiguity?
Scientific notation. It's the best way. 1 by 10 mental is clearly 1 sig fig. 1.0 by 10 mental is 2. 1.0 by 10 mental is 3. No ambiguity.
Okay, scientific notation for clarity. Good tip.
It really matters, especially when you start doing calculations.
Right, because the uncertainty carried through. There are rules for calculations too, aren't there?
Yep. Different rules for multiplication division versus addition subtraction.
For multiplication and division.
Your answer can't be more precise than your least precise measurement. So you round the answer to the same number of sig figs as the input number with the fewest sig figs.
Okay, limited by the weakest link in terms of sig figs.
Exactly.
And for addition and subtraction.
It's about decimal places. Your answer can't have more digits after the decimal point than the input number with the fewest digits after the decimal point.
So it's about the position of the uncertainty, not the total number of sig figs.
Right. You line up the decimal points, add or subtract, and then round based on the column where the uncertainty first appears.
At a crucial point for multi-step calculations.
Don't round until the very end.
Why is that?
Rounding errors can add up. Keep at least one extra digit in your intermediate steps, then round the final answer according to the rules. You can actually get slightly different answers if you round too early.
Right. Okay, so round only at the very last step.
It preserves the integrity of the calculation.
Let's think about that gas density example from the source. You might start with precise mass measurements, maybe 4 sig figs.
Right.
But if calculating the volume involves a subtraction that limits you to, say, 2 decimal places, which might only be 2 sig figs.
Then your final density, even if you divide two numbers that look precise, might only be reliable to 2 sig figs.
You have to track the uncertainty through each step.
Absolutely. It ensures you're honest about your results' precision.
This ties into accuracy versus precision, doesn't it?
It does. They sound similar, but they're distinct concepts.
Accuracy is how close you are to the true value, right?
Exactly. Are your measurements hitting the bullseye?
And precision.
Precision is about how close your repeated measurements are to each other. Are your shots tightly clustered, even if they're off-center?
The source uses that aspirin example. True mass is vol 0.370 grams.
Right. Student A gets like 0.335, 0.331, 0.333, very tightly clustered.
So precise.
But consistently low. Not accurate. Maybe their balance is off.
Okay. Student B gets results all over the place.
Yeah, like 0.357, 0.375, 0.338. Neither precise nor accurate, just messy data.
And student C
Gets 0.369, 0.373, 0.371. Tightly clustered and centered around the true value.
So both precise and accurate. That's the goal.
Ideally, yes. You generally need precision to achieve accuracy, but precision alone doesn't guarantee accuracy. Your instrument could be precise but faulty.
Good distinction. Okay, let's shift to actually using units to solve problems.
It's practical application.
This involves conversion factors.
Your best friend in chemistry calculations.
So a conversion factor is just a fraction that equals 1, basically.
Pretty much. The numerator and denominator are the same quantity, just in different units, like 1 inch and 2.54 centimeters.
So you can write it as 1 in 2.54 centimeters or 2.54 centimeters 1 inch.
And since it equals 1, multiplying by it changes the units, but not the actual value of the quantity.
Like converting 12 inches to centimeters.
Yeah.
You multiply by 2.54 centimeters 1 inch.
The inches unit cancels out top and bottom, leaving you with centimeters.
And since 2.54 centimeters per inch is an exact definition, it doesn't limit your sig figs.
Correct. Exact conversion factors don't affect sig figs.
This whole process of using conversion factors is called dimensional analysis.
Or the factor label method. It's super systematic.
You just chain the conversion factors together.
Exactly. Say you want inches to meters, you go inches to centimeters, then centimeters to meters, multiplying by the right factor.
Look at how units guide you.
They absolutely do. If the units don't cancel out to give you what you want,
You've messed up the setup.
it's a built-in error check. Track your units.
Like converting the FDA sodium limit, 2,400 milligrams per day, to pounds per day.
Yep. You'd go milligrams to grams using 1G 1,000 milligrams.
Then grams to pounds, using 1 pound 453.6 G.
Milligrams cancel, grams cancel, you're left with pounds.
What about units raised to powers, like volume, C-megawal, or emega?
Ah, good point. You have to raise the entire conversion factor to that power.
So if you're converting cubic centimeters to cubic meters, and 1 centimeters, 10 over 1
You need to cube the whole thing. 10 over 1 centimeter, that becomes 10 over 1 centimeter.
You have to convert each dimension. Makes sense.
Otherwise, your units won't cancel correctly.
All right, let's change gears again. How do chemists classify all this matter we've been measuring?
Broadly, it's either a substance or a mixture.
A substance. That's like pure stuff.
Exactly. A form of matter with a definite, constant composition and distinct properties. Think pure water, H2O, pure iron, Fu, salt, NaCl.
Its properties are always the same wherever you find it.
Right. While a mixture is a physical blend of two or more substances.
But they're not chemically bonded.
No, each substance in the mixture keeps its own identity and properties. Think salt water, air, nitrogen, oxygen, etc., trail mix.
And the composition can vary, right? You can have saltier or less salty water.
Precisely. Mixtures don't have a fixed recipe like substances do.
And substances exist in different states, usually solid, liquid, gas.
The three main phases we encounter.
Solids, particles locked in place, definite shape and volume.
Rigid structure.
Liquids, particles close but can move around, definite volume, could take the shape of the container.
Flowing.
Gases, particles far apart, moving randomly, take both the shape and volume of the container.
Highly compressible.
And crucially, you can change the state, melt ice, boil water without changing the substance itself.
It's still H2O whether it's solid, liquid, or gas. Just the arrangement and energy of the molecules change.
Okay, and mixtures can be classified further too.
Into homogeneous and heterogeneous.
Homogeneous means uniform throughout, like a solution.
Exactly. Salt water, clear apple juice, the air you're breathing, you can't see the separate components, they're perfectly mixed.
Whereas heterogeneous is chunky, not uniform.
Good way to put it. Trail mix is the classic example. You can see the nuts, the raisins, the M&Ms, sand and iron filings too. The composition varies from point to point.
And because mixtures are just physical blends?
You can usually separate them by physical means without changing the substances themselves.
Like evaporating the water to get salt back.
Yep. Or using a magnet to pull the iron filings out of the sand. The iron is still iron. The sand is still sand.
What are some other separation techniques?
Filtration, like with coffee grounds and water. Distillation, using differences in boiling points to separate liquids. Chromatography is a really powerful one, used a lot in labs.
Okay, so that's classifying matter. Finally, let's talk about describing matter through its properties.
How we characterize it.
We mentioned quantitative properties already, the measured ones with numbers.
Mass, volume, temperature.
And qualitative properties are observational. No numbers needed.
Right, like color, odor, texture, descriptive qualities.
Now, the big distinction. Physical versus chemical property.
Very important. A physical property can be observed or measured without changing the substance's identity.
Like color, melting point, density, its state at room temp.
Exactly. Observing these doesn't turn the substance into something else.
And a physical change is just a change in state or appearance, but it's still the same stuff.
Like melting ice, crushing a rock, dissolving sugar in water. It might look different, but the chemical nature is the same.
But a chemical property describes how a substance reacts, how it changes into something new.
Yes. You can only observe a chemical property during a chemical change, like flammability, you have to burn it to see it, or how it corrodes or reacts with acid.
And a chemical change then results in a totally new substance.
Fundamentally different composition. Iron rusting forms iron oxide, that's rust, a new substance. Burning wood creates ash, carbon dioxide, water vapor. Digestion breaks down food chemically.
You can't get the original stuff back easily by physical means.
Nope. The chemical bonds have been broken and reformed. Baking cookies involves chemical changes too, the baking soda reacting to make gas.
Interesting. Okay, one last distinction about properties. Extensive versus intensive.
Right. This is about whether the property depends on the amount of stuff you have.
Extensive depends on the amount.
Yes. Mass and volume are the classic examples. If you have more stuff, you have more mass and more volume. These values are additive.
2 blocks of wood have twice the mass of 1 block.
Makes sense.
But intensive properties do not depend on the amount.
Correct. They are inherent to the substance itself, regardless of how much you have. Temperature, density, melting point, boiling point.
So the density of copper is the same whether you have a tiny wire or a huge pipe.
Exactly. The temperature of a cup of tea is the same whether you measure the whole cup or just a spoonful. Intensive properties are often used to identify substances.
That's a really useful distinction. Okay, I think we've covered a lot of ground here.
We have. From the basics of matter and measurement to how we classify and describe it.
We've journeyed from big picture down to the nitty-gritty of sig figs and units and back out to properties and changes. Hopefully you feel you have a much clearer picture now.
Yeah, understanding these fundamentals really does give you a new lens to see the world. Cooking, medicine, materials, it's all chemistry. It really is that central science.
It connects so much. So thinking about all this precision, all the exact numbers chemistry relies on, here's a final thought for you. Considering how vital exactness is in science, how much uncertainty, how much inexactness do you think humanity can really tolerate as we keep pushing for more knowledge and progress?